if f goes from the ball into the complex numbers, and for every triangle so triangle means the boundary of the triangle, not the solid thing. We have that integral around the triangle equals 0. Then f is holomorphic. Okay, so what we learned before was that if f is holomorphic, a differentiable on an open set, then it follows that the integral around every triangle is equal to 0. So we prove this in the case when we have a ball, but it's true in more general sets. But this is the same situation. We have a ball, okay, and now we have that the integral around the triangle is equal to 0, and this implies holomorphic, which is the opposite implication. Okay, and you had this for homework for the special case when we just had equilateral triangles, but via a different method, we're going to prove this under the stronger hypothesis that we have all triangles. Okay, and this is how we're going to do this. So proof. So we have our ball. Okay, and we have that every single triangle, the integral is 0. So we're going to define the primitive, or we're going to define a function like this. For any z inside the ball, we just take this L shape like this, or the L shape like this, up to this thing. So let's call this guy whatever. Let's call it gamma of z. Yeah, or we could call this one, say, pi of z. Yeah. So proof. Define this function f of z to be the integral over gamma of z of little f of zeta d zeta, like this. Yeah? We could also define it to be equal to the integral over pi of z, because by the fact that we have integral of every triangle is equal to 0, it's going to be exactly the same thing. Yeah, that's how this proof worked, because since the integral of every triangle is equal to 0, if we go up, across, and then down like this, it's equal to 0. And if we go across, up, and then down like this, it's equal to 0. Yeah? So, let's take the right color, blue. So, this thing, this integral, yeah, is the same as going like this, yeah? Because this thing minus this part is equal to 0, yeah? So going like this is the same as going directly like this, yeah? And the same for this. If we go across like this, yeah, it's the same as going like this, because going across and then down is 0. So we can just go like this and get exactly the same answer. Yeah? Cool. So these things are the same, yeah? And therefore they're well defined. So there's no ambiguity about which we have to go left, or if you don't have to go horizontal or up or horizontal, it gives you exactly the same thing. So, a well-defined function. And exactly the little argument I just sketched means that if you try and consider f of z plus h minus f of z, right? This argument, which was the argument we saw before, means that this thing is going to be exactly the same thing as the integral from this line segment z to z plus h. All right? like this. Yeah? And this was breaking things down into triangles. We did this argument before. Yeah? So, just by the fact that this thing is continuous, which I didn't say, if continuous, the limit as h goes to 0, f of z plus h minus f of z over this is just equal to f of z. If you just write out the integral, we did this argument before. It's very straightforward. Yeah? So actually, capital F is the primitive. And the only thing we need about this primitive is just that capital F prime exists. Yeah? Okay. So since capital F prime exists, tell me why the theorem follows. Why does it follow that just having the integral around triangles being equal to 0 means that the function is holomorphic? Again, what do we know about capital F if f prime exists? Is it a nice function? It is C infinity. Why? Because capital F is holomorphic. Holomorphic is just having a derivative, yeah? So capital F has a derivative, it's holomorphic. And then all of the stuff that we know just kicks in for capital F, yeah? All of our theorems apply. So the instant, this is the first striking theorem of complex analysis. As soon as you have one derivative, then this whole kind of gift basket of good stuff just falls in your lap. You have infinitely many derivatives, like Father Christmas just turns up and gives you all these good things about your function straight away. Yeah, you have infinitely many derivatives. You have a Taylor series. Yeah, so capital F is holomorphic, and thus infinitely differentiable. Yeah? So, capital F prime, which is equal to little f, is also infinitely differentiable. i.e. holomorphic. And that's it. Yeah? Cool. All right, so we have this nice kind of converse of the first theorem that kicked things off, which was by reducing things down into smaller and smaller triangles, we proved that if it was holomorphic, then the integral around the triangle was 0. Now we know the converse. Yeah? Yeah? If around every triangle it's 0, then it's holomorphic. And one of your homework exercises was to do this for an arbitrary equilateral triangle. If we tried to do this argument for an equilateral triangle, it wouldn't work, right? We wouldn't succeed. We can't even define this thing properly. We can't define this uniquely because we need to be able to use any triangle. Yeah? So if our hypothesis were just that we have equilateral triangles, there's no way to do this particular argument. You see what I mean? Yeah? Cool. All right, so that's why we needed this extra thing. We needed to be able to use other properties to actually conclude this. Yeah? And not all of you did this homework question correctly, so I kind of want to give some details about how to do that. So, does not work. If we just had equal integrals. Equitriangles. So let's give ourselves this hypothesis that we have this is true just for equilateral triangles, every equilateral triangle inside the ball. But let's give ourselves an additional hypothesis. The second derivatives of the u and v exist. So this is what I mean. So if we just have and f of x plus iy is equal to u of xy plus iv of xy, and second derivatives of uv exist, that's not enough to conclude it's holomorphic, right? Because we can just take any two functions u and v, which are C2, and then just put this like this, yeah? And that's not going to imply it's holomorphic unless we have the Cauchy-Riemann equations, yeah? Yeah? So having the u and v have two derivatives does not mean this thing is holomorphic. We have to have some argument that if we have the thing vanishes on equilateral triangles, then this thing has to be holomorphic. So let me try and squeeze as much details as I can here. I raised the board. Let's try and work out how to do this. So the hint was to use Green's theorem. Green's theorem historically was the first theorem, but it's got a formulation that is less obviously understandable. So let's talk about divergence and Stokes theorems, which are exactly the same thing in two dimensions. So recap on divergence theorem. If we have given vector field, let's say W from omega into R2, omega is inside R2 itself, okay? Then the divergence theorem is as follows. So divergence of W is the first coordinate and the first partial derivative plus the second coordinate and the second partial derivative. That's what divergence means, yeah? And the divergence theorem says the following, that we integrate around this thing. I'm going to write dx, but x is now thought of as being in R2, so it's the two-dimensional integral around the solid thing. Yeah? That's the same as the integral around the boundary of omega of W dot product the outward pointing unit normal when we integrate with respect to one-dimensional length, which we discussed before, and I'm going to write it as H1. And what's the picture that expresses this? So if this is our set omega, okay, this is our vector field. These vectors are pointing like this, 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 like this. And we take the normal like this, 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 around the outside. That is the outward pointing unit normal. This is gamma of this thing. Well, then what happens when we look at this thing? So here, where the vector field dot product with the outward normal is positive, it means it's flowing out from the region. And here, where the dot product of the vector field with the outward normal is negative, it means it's flowing in. Yeah? So this expression here is kind of like how much is flowing through our domain, through the boundary of our domain. Okay? So if you think of W as being the velocity field of water, so imagine water moving around, then each point has a certain velocity field giving its direction. Then this quantity, integrating around the outside, is how much water is flowing out and flowing in. Yeah? And divergence theorem says that to understand this thing, we have to just calculate this thing, integrate this partial derivative, okay? integrate this expression involving partial derivatives. Yeah? And it's a generalization of the fundamental theorem of calculus, because the fundamental theorem of calculus is a very similar form, right? We integrate from a to b, derivative dx, and it's equal to f of b minus f of a. Yeah? So this guy is like this guy, because the boundary of the interval is just the points a and b. Yeah? So we think about this thing as being the generalization. So again, this thing is the special case of this thing, and I can show you why later if you want. And this thing is the special case of this thing. If you just take a vector field which just has one coordinate and you apply divergence on a rectangle, you get exactly back this thing here, right here. Okay. So this is the divergence theorem. And it has a kind of nice geometrical meaning. So in fluid dynamics, they talk about incompressible fields as being fields for which the divergence is equal to 0. If the divergence equals 0, you can see what that means. It means that you're not able to push more water into some particular closed region. You can't compress it. Yeah? Yeah? So the word incompressible makes sense so the word incompressible for vector fields whose divergence is 0 makes sense given the nature of divergence theorem. Yeah? Cool. So Stokes' theorem is at least in the plane, is very similar, except that now we're going to integrate not with the normal but with the tangent. Not with the normal but with the tangent. Yeah? And if we do that, then this is Stokes' theorem. So let's do curl of a vector field W is minus dW W1, W2. So we're going to do minus W2, 1 plus W1, 2. Okay? And then Stokes' theorem is that when we integrate like this, the curl of W dx, that's the same as taking the integral around the boundary and taking W, and this time we dot product with the tangent T of x dh1, the tangent around the outside. Okay? And it's the same thing as divergence theorem, because all we've done here with this curl is we've flipped things around. So what I mean is that if we take a vector field and then we flip it around to being 90 degrees perpendicular to it, and then we apply the divergence, that's the same as doing the curl to the original vector field. Yeah? So if we take a vector field, so this is our vector field, and this is the vector W1 of x, W2 of x. If we want to get a vector field that's perpendicular to it, then we can do this. We can do minus W2 of x, W1 of x. That's perpendicular. Yeah? And then if we apply the divergence to this perpendicular one, that's the same as doing the curl to the original one. You see what I mean? Yeah? So if we take a vector field W and just flip it around to make a perpendicular vector field and apply the divergence theorem, then the divergence becomes the curl, and this thing becomes now the dot product with the tangent instead of with the normal. Because if we flip the normal by 90 degrees, then it becomes the tangent. Yeah? So Stokes' theorem is the same as divergence theorem in the plane, and Green's theorem is just Stokes' theorem. Okay? Cool. All right. So this might be known to you, maybe not, but just in case not, I wanted to clarify this. We are going to try and prove that we have this function for which we have the integral around these triangles are equal to 0. Yeah? And we're going to try and prove that it's actually holomorphic. So what do we have? We have that f x plus iy equals u of x, y plus iv of xy. And let's write out what this integral around the triangle is. So pick triangle. So I'm going to write equitriangle. In the ball. And let Z of t be a parameterization of the triangle. So I'm going to write from 0 to t, going into triangle. Bad choice. From 0 to a. Going into the triangle will be a parameterization. Then, what do we do? Well, the integral around the triangle of f dz is the integral from 0 to a f of z of t, z prime of t, dt, right? And what's this? This is equal to the integral from 0 to a of u of z of t plus iv z of t z prime of t dt, like this. Yeah. So let's draw a picture of the triangle. So let's write like this. So z of t has got coordinates z1 of t plus the imaginary coordinate z2 of t. Like this. Yeah? So z prime of t equals z1 prime of t plus I z2 prime of t. And let's put that stuff into this. So that's equal to the integral from 0 to a u of z of t plus iv z of t. And then here we've got z1 prime of t plus I z2 prime of t, like this. Yeah? dt. Cool. All right, let's look at this thing. If we multiply through and collect up the real and imaginary parts, what do we get? We get 0 to a. So we're going to have a real part from this. We're going to have u of z of t, z1 prime of t. An imaginary part from this, we're going to have v z of t. Oops, there'll be a minus because I times I, z2 prime of t. And then this thing here is, we're going to have a v z of t, z1 prime of t, and we have plus u z of t, z2 prime of t, right? dt. Yeah? And this all stuff is equal to 0 because that's the hypothesis, right? So this is equal to 0. So that means both the real and imaginary parts of these integrals are equal to 0. Yeah? So this part right here, let's call that a. When we just integrate this with respect to t, it's equal to 0, and this part right here, when we let's call this b, that part's also, when we integrate it with respect to t, is equal to 0. So let's just look at this individual expression right here. So a is equal to the integral from this thing, and let's write this as the dot product of u of z of t let's do minus v z of t like this, dot product with z1 of t, z2 prime of t like this. That's what this expression is, dt. And this thing is equal to 0. Yeah? And b is the integral from 0 to a of this expression. Again, we're going to write it as the dot product. So we're going to write v z of t, and then u z of t, dot product with this thing. So we're doing this because we know that the hint is to apply Green's theorem, Stokes' theorem, divergence theorem, whatever. So we have to turn it into a real integral around the boundary and see what form we get. Yeah. Once we put it in this form, then what we notice, so this is the parameterization. So we know that when we take the derivative, z prime of t, it's going along the curve, right? It's going to be the tangent to the curve. Yeah. We can actually make this the arc length parameterization so that this has got a unit vector, so it's exactly the tangent to the curve. Yeah? You see what I mean? Yeah? So, then this is exactly in the form of Stokes' theorem, right? We're taking some vector field, we're integrating the dot product of the tangent to the curve with the vector field. Yeah? Yeah? Do you see what I mean? Nod your head if you see what I mean. Give me a thumbs up. Okay, so A is also equal to the integral around the solid triangle. So let's call it the convex of the triangle. The convex hull, recall, it's a set of points we get from linear combinations, right? So if we take the convex hull of the triangle, it's everything we get from taking any line that joins it. So we fill out the entire thing, yeah? So that's just a way of saying the interior of the triangle. Yeah, just notation I used before. So this thing is going to be equal to the curl of this vector field, u, and now we're going to write it. We're just going to write u and then minus v like this. And I'm going to write dx, where dx means the integral over the two-dimensional thing, right? So, yeah. So this thing is equal to the curl. And what's the curl? The curl is the integral in the convex hull of okay. Maybe I don't want to write x because I fear it's going to confuse you. So I'm not going to put anything here. I'm just not going to put anything here. Like this. Okay, I feel bad about doing that as well. Oh, damn it. All right, so I compromise. I'm going to write dx dy. Dx dy. Okay. So that's what this is, yeah? And that thing has to be equal to 0. Yeah? Same game here. What is this thing? Again, we're going to apply Stokes' theorem. This is the tangent. So then this thing is equal to the integral around the convex hull. Let's do the double integral of t of the curl of this vector field, which is v u, okay? And then dx dy. Yeah? And what's that? That's the double integral around the convex hull of t, and then it is ux minus ux plus v of y. This is vx. Okay, and so it's minus the second coordinate with respect to the second partial plus the first coordinate with respect to the second. Start again. It is minus the second coordinate with respect to the first partial plus the first coordinate with respect to the second partial. That's what curl is. So minus the second coordinate with respect to the first partial is this thing, is this thing. Yeah? Cool. And then the first partial with respect to the second partial derivative is this thing with a y right here. Good. And then when we set this equal to 0, we do indeed get this thing, which is what we want. And we set this equal to 0, we get this thing. Okay, cool. So if this was equal to 0, and if this was equal to 0, then it would make sense, yeah? It would make sense, yeah? But that's not what we have. We have the integral around a triangle of these things is equal to 0. And what we'd like to conclude is that actually this is the case. Okay, cool. So since this is true for every triangle, this implies that v of x equals minus u of y, and the same thing here. And this implies that u of x equals v of y, and therefore we have the Cauchy-Riemann equations, okay? And it's a theorem I didn't tell you. It's actually a nice homework exercise, that if you have the Cauchy-Riemann equations for some function u, where the derivatives are continuous, then you can actually prove that that thing is complex differentiable. Okay, so we prove that if it's complex differentiable, it satisfies the Cauchy-Riemann equations. It's also true that there's exists a converse.